Are you looking for a comprehensive explanation of concurrency, including key concepts like multithreading, reactive programming, asynchronous and parallel programming, with a deep dive into async await keywords? Then welcome. I'm going to explain everything you need to master concurrency in my YouTube channel, and it is going to be the first tutorial that will start your journey. Before we get started, one quick thing. Don't forget to subscribe my channel. If you like my videos, hit the like button and share if possible. Now, let's rock and roll. Before diving into details, let's check what we have in our agenda. We're going to talk a lot about concurrency. We're going to learn the types of concurrency like multithreading, parallel programming, asynchronous programming, and reactive programming. At the end, you will understand what is multithreading, what is parallel programming, what is asynchronous programming, and the differences between these concurrent types. And at the end, I am going to explain async await keyword usage in C#, but not just usage, but also the behind-the-scenes operations, including async state machine in C#. We are going to talk a lot of interesting stuff. Stay tuned. As I mentioned before, everything is really easy to understand if you have a good mentor to explain it. Okay, let's learn about concurrency. Concurrency is doing more than one work at a given time. Do one thing while the system is working on another thing. It is crucial for improving responsiveness and performance in modern applications, especially those dealing with input-output bound operations or user interactions. This is really easy topic. So this is our diagram. In our diagram, we have a user, and user has two requests. The first one is going to be the database request, the other one for external service. So for the first request, when user requests to the database, we have some type of operations behind the scenes. We are doing, for example, bulk insert to the database. Meanwhile, it is possible for our user to request to the external service. The long story short, while finishing the first request, it should be possible for us to respond to the second request. This is another diagram. In this diagram, we have two operations, including upload to server and get from the database. While uploading to the server, it is possible for us to get data from the database. Actually, we are doing more than one work at the given time. That is actually what we are calling concurrency. Well, let's talk about the implementation forms of concurrency, but before that, I want you to understand that concurrency is a general concept. It means it is possible in .NET to implement concurrency using multiple ways like multithreading, asynchronous programming, reactive programming. So the concurrency, you can compare it like architectural style. You have architectural style in a high level, and it is possible for us to implement given architectural style using more than one ways. So in .NET, we have more than one way of implementing concurrence, and one of them is actually going to be our multithreading. What is multithreading? Multithreading is a type of concurrency, and it is a specific approach used to achieve concurrency within a program. In software development, multithreading is a technique that allows multiple parts of a program to execute concurrently within a single process. In modern software development, we're using thread pool to enable multithreading. Actually, you can use thread as a class in your application, but when you have a thread as a class in your application, it indicates that you are dealing with a legacy code. So don't use thread, instead use thread pools. And multithreading is equal to multiple threads within a single process. We often use multithreading for CPU-bound tasks or parallel processing. Remember that parallel processing is equal to parallel programming. The parallel programming is a type of multithreading. We'll talk about it. And multithreading allows multiple threads to share a single CPU and execute one after another, creating the illusion of simultaneous execution. So in general, we have multithreading, and it is a type of concurrency. Let's talk in detail about the multithreading. When you create a console application, Windows Forms, WPF application, doesn't matter, you will have one process, and by default, you will have a thread called main thread, whatever you can call it. So what is a thread? Thread is a single sequential flow of control. Okay, so in our process, we have one single thread. But when we want to deal with simultaneous operations, when we have multiple operations and we want to run them simultaneously, we are going to create multiple threads. So we have one main thread and multiple worker threads. Let's talk about the old school implementation of multithreading. In old school, we have one CPU with one core, okay? And if we want to run more than one worker thread at the same time in one core CPU, actually, from the physical perspective, it is not possible. But in CPU, it is possible for us to do more than million works in a given time, trillion even works. So the CPU will somehow create a simultaneous operation. From the user perspective, it will look like the exact simultaneous operation, but from the CPU perspective, there is no simultaneous operation in one core, because when you have more than one thread, we are dealing with time slicing, and we are dealing with context switching between these threads. We'll talk about multithreading in more detail in our other tutorials, but for now, the brief information is enough for us to understand multithreading. Actually, I'm not going to explain multiple cores, because after that, we'll have the parallel processing explanation, and in this case, we'll talk about the multiple cores. But for multithreading, it doesn't matter if you have one core or 10 cores in your CPU. When you have more worker threads than your cores, then you will deal the false simultaneous. It is actually from the user perspective, as I mentioned, the simultaneous operation, but from the CPU perspective, it is not a true simultaneous operation. Okay, now it is time to talk about parallel processing. Parallel processing is actually parallel programming. It is a type of multithreading used to achieve real parallelism. As we mentioned before, in multithreading, we have the fake parallelism, but using parallel processing, it is possible for us to achieve real parallelism. Okay, we can think about the parallel processing like updated version of multithreading. Actually, you can call parallel processing a type of multithreading, not just type of multithreading, but some implementation of multithreading, okay? The parallel processing is a specific type of multithreading that focuses on achieving true parallelism by utilizing multiple CPU cores and multiple tasks at the same time on different CPU cores equal to parallel processing. So we have this type of diagram, we have concurrency. The type of concurrency is going to be our multithreading, and the type of multithreading is going to be our parallel processing. We have another diagram, like in our multithread environment, we talked about the old school snapshot. Now we have modern snapshot. In our application, we have again multiple threads, one main thread and multiple worker threads. And in our CPU, we have multiple cores. Now we have 4 cores, and I have 4 worker threads. Now it is possible for me to assign worker threads, one worker thread to one core. Now you have 4 cores and 4 worker threads. You will gain a true parallelism in this case. But how about when we have more than 4 threads in this case? We have 4 cores and we have 6 worker threads. In this case, system will try to parallelize things, and we'll try to assign other threads to the cores. In this case, for example, core 1 and core 2, we have 1 worker thread. They have true parallelism. For core 3 and 4, we have 2 worker threads, okay? And in this case, per core, like core 3 and 4, we have fake parallelism. We have context switching between these threads. That actually we have, again, multi-threading in this case. So the parallel processing is just a form of trying to use all possible cores in our CPU to make the things a true parallelism. However, it's time to talk about asynchronous programming. Asynchronous programming is a type of concurrency that uses promise, future, or callbacks. We have task and task result as a future types. And actually, in asynchronous programming, we have asynchronous operation. What actually asynchronous operation is? Asynchronous operation is an operation now underway with completion expected shortly. So you have some type of operation, running operation, and you are waiting the response from this operation in near future. This is actually an ongoing operation. In general, we have asynchronous code using delegates, events, and futures. We are using asynchronous programming for input-output bound operations. So we have two types of operations in general. We have CPU bound operations. We have input-output bound operations. We are using multithreading and parallel programming for CPU bound operations. We are using asynchronous programming for input-output bound operations. So we have network-based queries. We have database, working with files. All these operations in general are input-output bound operations, and we are dealing with them using asynchronous programming. So we have different forms of implementations of asynchronous programming. We have in old school, in .NET 1, we have asynchronous programming model using delegates. In .NET 2, we have event-based asynchronous pattern, EAV. We'll talk about it also, but in another tutorial. And we have async await and new task parallel library that helps us to deal with asynchronous programming. So, in general, what is asynchronous programming? Let's say you have some type of application and we have a main thread. And in this main thread, I am requesting to a database or to external service. It doesn't matter. So the purpose here is I don't want to block my thread. In the server applications like ASP.NET Core applications, I don't want to block my request thread. For the UI applications, I don't want to block my main thread. It is called UI thread in Windows Forms or WPF. So you don't want to block your thread. You want to gain responsiveness, scalability, and it is possible to do it using asynchronous programming in our case. And one of them is actually going to be using async await keywords in asynchronous programming. So in general, we have this type of scenario. We have concurrency, and for now, we have two types of concurrency: multithreading, asynchronous programming. Actually, the reactive programming is also another type of concurrency. It is possible to implement reactive programming using concurrency, but this is not a 100% requirement. But anyway, and we have a type of multithreading called parallel processing. Okay, but how about reactive programming? Reactive programming is also a form of concurrency, but that it is using asynchronous events. So in asynchronous programming, we are using asynchronous operations. Okay, we have callbacks, future promises. They are together calling asynchronous operations. But in reactive programming, we have asynchronous events. It doesn't always have a defined beginning, might occur at irregular intervals, and might happen multiple times. This is how the reactive programming is working. So in general, we have an application and we have some type of events that we need to react. It is possible to use reactive programming without multitasking. So you can include reactive programming to type of concurrency, or you can exclude it. But in general, it is possible to implement reactive programming using concurrence. For that reason, we are including the reactive programming to a type of concurrency. And at the end, we have this type of scenario. We have two implementation ways of concurrency: multithreading, that we are using for CPU-bound operations, and parallel processing. We have asynchronous programming. We are using them for input-output bound operations. And we have reactive programming. We are reacting to a lot of events in our application. And we have a subset. We have a type of multithreading called parallel processing that helps us to parallelize, to use all the possible CPU cores in our application, in our system, to help us to gain true parallelism. Well, it is time to explain async await in practice. I've created a simple console application for you. The purpose here is provide a really easy example first to decompile and get the real async state machine from that. And the second one is really easily understand async await. For that reason, I haven't provided the real world examples. But after understanding this topic, you can easily create your real world example and decompile and try to investigate. I have really simple two operations here. The first one is sum, that sums two numbers, and the calculate that calls sum and prints a message, some messages using console write line. So they are actually synchronous operations. So our main thread will be blocked by the calculate, and calculate will be blocked by the sum. So we have, in general, this type of structure. For the calculate functionality version 1, we have calculate and sum. They are blocking operations. Main thread blocked by calculate, calculate blocked by sum, and when we retrieve whole information from calculate, the main thread will continue working. This is really easy. Let's just run and see what we are getting at the end. So we have synchronous flow. First, we'll print operation started. Then sum is running actually, and the third message is going to be the result is blah blah, and the fourth one is operation finished in thread 1. So we have one single thread that handles all these two operations. This is really easy. So let's switch to the second version of this operation. Well, in our version 2, I have a slightly different implementation. For the version 2, I have the same console write messages, but now I'm not calling the sum method directly. I'm encapsulating it to the task, and using task factory struct new, I'm running this task and getting the instance of this task. And from the task, I'm getting the task awaiter. And for the task awaiter, I'm calling uncompleted. That will notify our main thread, our main console thread, after the operation done. So we are encapsulating our sum. We are not going to run sum in our main thread. Instead, we are encapsulating it to another task and running it. That's all. And our main thread is free to continue to work. It means when we print operation started, it will be possible to us to print operation continues after this message instead of seeing it at the end like typed in our calculate version 2. Let's run our calculate version 2 and see what happens. In my case, it should print first operation started and then operation continues. Why this? Because our sum method encapsulated to another task and run in a separate manner. We are not running it in our main thread. We'll talk about how asynchronous operation runs, but for now it is enough to understand that we are not running it in our main thread, and for that reason our main thread is free, so we are easily moving to operation continues, and we are providing a delegate. We are providing a delegate to uncompleted method, and sum executes, and after that, when operation is done, we are getting notification like operation finished in thread 7. So we have different thread for this task and the main thread with number thread ID. We'll talk about why we are getting this type of different threads. Actually, this is going to be our asynchronous operation, but in this case, we have a little bit problems to write it, because every time when we write our asynchronous operation, we need to somehow to wrap a task. We call task awaiter uncompleted. This is really annoying. So using async await, actually we are planning to implement it in version 3. It should be possible for us to create asynchronous code like in our synchronous code. Let me just copy our synchronous version of calculate. Okay, I will show you how it is easy for us to convert our synchronous operation to asynchronous operation. Okay, so let's call it calculate version 3. Instead of calling sum, I am going to implement asynchronous version of this sum. So let's call it async sum async. And for the sum async, what I'm going actually to do is task dot delay and time span dot from milliseconds 10. That's all. That's actually is a simulation of asynchronous operation. If you want to simulate asynchronous operation, you can easily call the task delay. Task delay is our awaitable operation. For that reason, I am calling await here, as your guess system automatically generates async keyword. Let's call control ADK, and let's format it. And after that, so we have async await keywords, but we have some issues here. The problem here is when you await your method in your signature, you should provide async. And if you return some value, the returned value should be wrapped to task. So it should be task decimal. So you may ask why we are wrapping our decimal return value to a task, but we are returning the exact decimal here. The problem here is the async await will be converted to async state machine, and in this state machine, the rest of code after await is going to be our continuation task. For that reason, this is actually wrapped to task, and we are returning task decimal rather than decimal. Okay, we have some type of simulation here. You can actually call any awaitable signature method in this case, but to simulate it, I'm using task delay. And to call some async, what I'm going to do, I'm calling some async with awaitable keyword, of course, and I need to modify my calculate to have async keyword with task. Actually, async task or async void, which one to use. For event-based cases, for events, use async void. I will show you one example in our further videos, but for now, just understand that in approximately most cases, we are using async task. Such type of library-based implementation, your custom implementations use async task. But for the event-based things like in WPF, like in Windows Forms, for the asynchronous events, you should use async void. Okay. Cool. Now we have asynchronous method. So we converted our calculate to calculate version 3, and version 3 is really asynchronous operation. So what is the differences between calculate and calculate version 3? From the signature perspective, they are 90% similar. So we are avoiding this void, we are using async task, and we are just using await instead of just synchronous call. That's really easy. The purpose of async await was first to create asynchronous code like a synchronous one. There is no need to create thread tasks to do some type of wrappings over your synchronous code. So it should be really easy for us to create asynchronous operations like synchronous ones. And the other one is the asynchronous code helps us to make a responsive application, especially for the UI-based applications. Our main thread is free to serve another requests. And from the scalability perspective, it is really easy to scale this type of applications. Now we have calculate version 3 and some asynchronously. And that's all. That's the real implementation behind the async await. But let's try to understand how behind the scenes async await is working. Okay, now let's run our calculate version 3. Our calculate version 3 is actually asynchronous operation. For the main, we need to add async await keywords, and for the void, let's replace it to task, and let's run our application. So cool, now we have operation started, some is running in the thread 10, the result, and operation finished in thread 10. So we have our operation starts in our main thread, and somehow then we are handling this operation in another thread. How? Actually using async state machine that we are going to talk about. Now let's see, in our calculate version 3, we have await keyword. Okay, in our main thread, we also have await keyword. Now let's decompile it and see how the things will be visible from the .pig perspective. So I have .pig application here. Actually, it is really cool tool to decompile our application. Let's just open folder and let's go to bin debug.net and let's open our async await demo exe file. And let's go for the code program CS, and let's go for first calculate and calculate version 2. For the calculate and calculate version 2, I have string information. For that reason, it is using default interpolated string handler. It doesn't matter for us. So we have approximately same code in our calculate and calculate version 2. But we are observing a different type of implementation in our methods where we have await keyword. So for the calculate version 3, we have await. For the main, we have await. Let's go for the calculate. For the calculate version 3, I have some type of state machine builder. Wow, really complex stuff from the first glance. Okay, so let's go for the main method implementation and see if it is applicable for main also. Oh yeah, it means we have state machine generation where we are using the await keyword. Okay, let's dive into details and try to understand what happens behind the scenes. When you create async await keyword in your application, when you're using asynchronous programming using async await, actually when you await your code, it is automatically generates asynchronous state machine. This asynchronous state machine actually consists from a builder. Let me show you. So we are instantiated. So we have calculate version D__3. It is actually our async state machine. In old .NET versions, when you compile your code, you will realize that you have direct async state machine instantiation here. But in our case, in .NET Core latest version, I'm using .NET 8. In this case, I have async state machine as an attribute, and we have some type of class here, and we are instantiating our state machine. For the state machine, I have a builder. State machine is a class. It has a builder property. Okay. We are creating async task method builder that create. Using this create, we are setting the value for the builder. We are providing first number, second number, and our state machine's first state is going to be -1. It is really important. And for the builder, we have start. We are starting this builder, okay? And this builder accepts state machine as a reference value. It means our state machine knows about the builder, and builder knows about state machine. So we have bidirectional communication between these elements. So in general, async await behind the scenes uses two design patterns, two general design patterns, state machine pattern and state pattern, and actually the builder design pattern. And let's see what happens when we call builders start. We have async implementation, async state machine. Let's check. We have async state machine implementation. This is our compiler generated class. As you remember, calculate version 3D -3. It implements async state machine, and this async state machine, we have move next method. Actually, when we call builders start, it will automatically call our move next. And this move next in our state by default, we have -1. Okay, and we are checking if the num1, this is a generated name, it doesn't matter for us. If the first state is not equal to 0, in our case, it is not equal to 0, it is -1, then system is going to do some operations with awaiter, get awaiter. Okay, we are awaiting response from some async method. Okay, and the important thing here is we are calling is completed. If it is completed, it has a different flow. If it hasn't been completed yet, it has a different flow. Otherwise, it has completely different flow. It means when a waiter is not completed, we are going to call move next again. This await unsafe uncompleted will call our move next again with setting its state to 0. That in the second time it is going to check if it is equal to 0. Yes, then it will switch to continue the further stuff here, like including else and the further stuff here. Okay, and I'm going just to copy this functionality from here and implement it in our C# code. Okay, I have copied the source code from the .pic, from the EL viewer here to my console application and did a little bit refactoring. Actually, I named the wrong classes, the wrong field names. Now we have properly working application. Let's run this application and see everything is working properly. And what we have now, we have actually our async methods with async state machine attribute. We have calculate version 3, we have some async. For them I created, for example, some async. I created some async state machine. For the calculate version 3, I renamed it to calculate version 3 state machine. In all .NET, they are using async state machine class instance, but in .NET Core, we have automatically generated async state machine attribute with the proper type. Let's go for our type. All our state machine class types inherit from our async state machine. This is our main interface to implement state machine for async await. It has move next and set state machine methods. Actually, when as you realized, for all type of our async methods that call await keyword in it, we have approximately same calling structure, same method structure. Let's take, for example, our calculate version 3. In our calculate version 3, we are instantiating the instance of state machine. For the state machine, we are creating a builder. Actually, state machine has a builder property, and the builder already knows about state machine. As I mentioned, we have bidirectional communication between state machine and builder. We have first and second numbers in our state machine. Actually, it is code generated, so automatically it is creating the first number and second number properties fields in our state machine. And we have, this is really important, we have state by default -1. Okay, and when the builder starts, it actually calls our async state machine's move next method. Let's go for the move next method. In our move next, the builder's start will call our move next. Okay, in our move next, we have some type of logic. We are calling our some async, okay, with a waiter, and we have special checking here. And if the awaiter isn't completed, we will call the move next for the second time. This is really important to understand that when our move next starts first time, it starts with default value equal to -1. This is our -1, and in our if we have number 1 equal to -1. So for the first call, we will go to this part of if, and we will try to get a waiter from our some async to check if a waiter is completed or not. If is not completed, we are going to call move next for the second time, but with state equal to 0. This is really important. For the second time, move next will not go to this if. Instead, it will run else and the rest of stuff written here. So let's check. I'm just putting the breakpoint here. Let's put breakpoint to our try. Okay. So in my code, in calculate Let's go to main, our main. We have main state machine. Okay, we are debugging our main state machine. We have approximately same structure for all waiters, so there is no big difference between these state machines which want to debug. For now, I'm debugging my main state machine. For the main state machine, we should see the -1 by default here, and for the second time it should be 0, and it should be called twice, because when we, let's go to our main method here, in our main method using the builder's start, we are running the move next for the first time, and in move next itself we have await unsafe uncompleted that will call this move next for the second time, but with state equal to 0. Okay, so let's go to our application, let's run it. So in my num1 I have -1. This is the first time to call our move next. Okay, let's debug it. Let's continue. So we are entering to this if. We are getting the calculate, checking if awaiter is not completed. It is not completed. The state is equal to 0. Okay, and using await unsafe uncomplete, when I click continue, you see we are calling the move next for the second time with num1 equal to 0. That will jump to else and for the further operations here. That's how actually internally async await works. Actually, there are some type of few differences between async await in console, in WPF, in ASP.NET Core applications. We'll talk about them, but for now, we are trying to understand internally how async await works. So in general, async await generates async state machine behind the scenes, and it uses state and builder design pattern in this case, and using this move next for the second time for the await unsafe uncompleted, it will call it in another thread. That's why for the first time, let's check it, for the first time when we run our main application here, our main state machine, all these instructions, like for example, let's go to the original source code to explain it. When we call our calculate version 3 asynchronous operation, this will be run synchronously and actually in our main thread until it reaches to await keyword. This is really important, and the things after await is going to be a task continuation and will be visible in another thread, will be catched by another thread actually. So let's try to run our application again, and let's call the calculate version 3 to check if everything is working properly. We are starting in thread 1. This is our main thread. We are running some in thread 11. Actually, in thread 11, we are catching this information, and for the operation finish it, we are catching it for the thread 11. Why? Because we have, let's see what we have here in our await compiled application. We have two types of move next calling. The first move next calling will be happen in our main thread, in our original thread, and the second call, the await unsafe uncompleted, the previous versions of .NET, it was just uncompleted, I guess. Yeah, it was await uncompleted, but now it is await unsafe uncompleted. Yes, and we have simple check here. It is also important. If your awaitable operation is already completed, then there will not be another thread. In this case, let's go to our calculate version 3 original application. What I am actually going to do, I am going to return task dot from result. It means the operation is already done here. Let's await it, and let's try to run and check if we have another thread ID indication here. Let's see. You see, we are running calculate version 3, but all the operations are catched by the main thread in this case. Actually, as I mentioned before, there is no thread in asynchronous operation. I will talk about this in our next lesson. But for now, just remember that when you are having a waitable operation that is already done, this will not call the move next operation, and it is not going to move your rest of rest of the things after await to the next thread environment, let's say. So we mentioned that there is no thread in asynchronous operations, but let's try to understand what happens behind the scenes. We have main thread that starts the asynchronous operation by calling a waitable keyword. So we are using, for example, in calculate version 3, we are calling the await for some async. It doesn't wait for the operation to complete. Our main thread doesn't wait for the operation to complete. Instead, it suspends execution at the await keyword and returns control to the runtime. So we have between us and the operation system, we have a runtime. Okay, the operation system is primarily responsible for monitoring and handling the asynchronous operations progress. It notifies the runtime when the operation completes. So we are doing this type of asynchronous operations in operation system level, okay, in general, and operation system monitors and handles all the things related to asynchronous operations and notifies our runtime. When the operation finished, the runtime schedules the continuation of async method. So in the first time, the main thread suspend execution, and now after receiving response from the operating system, the runtime schedules the continuation of async method, and this continuation can execute on the main thread or a thread pool thread. So depending from the console application, WPF, ASP.NET, or your Windows Form applications, we have the continuation in our main or a thread pool thread, and also it is possible for us to configure it. So that's actually all what happens behind the scenes of async await keyword.